Okay, so I want to talk about basic homotopy theory. That's the title of this lecture. And I guess this writing is fine. Um, so if you don't understand, you can ask me in the middle. So the point of the homotopy theory is uh, so we want to study topological spaces up to homotopy equivalence. Okay, so that's the so if you so whatever I am going to say is the main reference for this is you can look at the chapter 4 of Hatcher, and so it starts by defining homotopy groups. Homotopy equivalence, of course, is defined much before, but it starts by defining homotopy groups and basically talks about topological spaces. Um, but something is happening, and the my screen is going away. Okay, so here it is back. So, so I want to talk about topological spaces up to homotopy equivalence. But I mean, if I just talk about, if I just talk in these terms, then then you would be wondering why. So why? How does algebra come into the picture? Because our workshop is also about. It will also have things in commutative algebra. So, so actually, this kind of homotopy theory, just studying topological spaces up to homotopy equivalence, was homotopy theory around 70 years back. But later, what happened is you you start thinking about topological spaces up to homotopy equivalence, and then you realize that you can you can define some you can define abstract um, homotopy theory. So you can isolate the axioms and you can do something what is called abstract homotopy theory. We will see that in our lectures, in the upcoming lectures. And then you realize you realize that this is applicable in other fields as well, that this is applicable in other categories. You realize that this is applicable in other categories. Okay, so categories coming from algebra or categories coming from algebraic geometry, you see that you can use stuff from abstract homotopy theory to analyze them. And so, I mean, you can use these tools to study categories with special kind of equivalences, with special kinds of equivalences. Okay, so so my lecture is also kind of organized from that point of view. It'll it'll give you the features what is needed to define this abstract homotopy theory. Okay, so that's what I mean. These kind of things will happen in the later lectures. But so today I will do this first thing, studying topological spaces up to homotopy equivalence. So that's my lecture today. And later on, you will see that it fits into a bigger story in the later lectures. Okay. Okay, so the homotopy. So I should start really by defining what are homotopy of maps. So if you have two maps, so you have topological spaces x and y, and you have two maps fg. I should rather I'll draw it like this. You have a map f. Map means continuous map for me. So what is a homotopy between f and g? So a homotopy h is a map from x cross 0 1 to y, such that if I look at x cross 0 inside x cross 0 1, this restriction is the map f, and if I look at x cross 1 inside x cross 0 1, this restriction is the map g. Okay, okay, so that's the homotopy. And you realize that homotopy between maps is a equivalence relation. So you define this to be the set of homotopy classes of maps. Homotopy classes. Maps from x to y. Okay. Uh, Also, some notation we always use top. This denotes the category of topological spaces. Topological spaces, and we also use. Actually, we will use this more often. Top star. This is the category of uh, based topological spaces. So topological spaces with a base point. Okay. So that means if I want to talk about homotopy of maps in top star, that will be homotopy of based maps. So homotopy, like, it should take the base point to the base point cross 0 1 to the base point. So I will denote by, I'll put a star. This will denote the based homotopy classes. Classes. Okay. Um, so so we will mostly use the based category instead of the top. Just instead of just top, we will use the based category. And okay, so the next thing is, of course, homotopy equivalence. Homotopy equivalence. So this is a map. So x f from x to y is a homotopy equivalence if there exists g from y to x, such that um, if I take g circle f, this is homotopic to, so that stands for homotopic to the identity map of x, and f circle g is homotopic to the identity map of y. Okay, that's homotopy equivalence. Okay, and so our idea is, we want to we want to understand when things are homotopy equivalent or not, and a good method of doing that is through invariance. So if you if you do a first course in algebraic topology, would that's the philosophy where you define fundamental group, then homology, then cohomology. Those are various invariants which can distinguish spaces that are not homotopy equivalent. Okay, so and the and one of the main invariants later on is homotopy groups. Homotopy groups. So, so you define uh, so X is a base space now. X is an object of top star, um, and pi n x is going to be the homotopy classes of maps from Sn to X. So Sn is always going to stand for the base space. So Sn for me always refers to the one point compactification of Rn, and the base point is the point at infinity. Always, so it's always fixed as a particular based space. That way there is no confusion. So this is the definition of homotopy group. So n is greater than equal to 0, you see. Now, this when you define it like this, you readily realize I will not prove all these facts. I mean, they are standard facts. You can see it in Hatcher's book, for example. The proofs are not difficult, but I don't have a lot of time, so I'll just go over them in very quickly. So pi 0 of x is the set of path components of x. Components of x, and pi 1x, this is called the fundamental group. This is the fundamental group of x. Fundamental group. So it has a group structure, but the group is not abelian. But pi n of x is an abelian group if n is bigger than equal to 2. Okay, so the homotopy groups, n equal to 0, it is just a set. N equal to 1, it's a group, but but may not be abelian. And n greater than equal to 2, it's an abelian group. All right. Okay, so the basic thing, one thing you realize is if X is a nice space like a CW complex. Uh, okay, I haven't defined CW complex as yet. Um, so maybe I'll start by defining that. So we define a CW complex. Uh, okay, so CW complex is a space X together with a filtration. Uh, X is equal to union k greater than equal to 0 xk. We write it like that. So filtration means I demand that xk is contained in xk plus 1, and xk plus 1 is obtained out of xk by attaching obtained out of xk by attaching k plus 1 dimensional cells. K plus 1 cells. Okay, so what that means is you you have some attaching maps, disjoint union of some boundary of dk plus 1 indexed by some indexing set to xk, and then you attached the interiors and you take the push out. That would give you xk plus 1. Okay, so that means this is a push out. So what does that mean? That means that um, that means you have these maps from the boundary of the cells, and you are taking the union of the interiors along those maps. Okay, and then there is a condition which I'm not mentioning, which comes up if I am looking, if this I mean this if the cells go all the way up to infinity, there is a condition that you are it has to be given the co-limit topology. Okay, so that means a cell is open if and only if its intersection with xk is open for all k. That let's not bother too much about that. So that's a CW complex. It's what is our category of nice spaces. And okay, now back to homotopy groups. Um, so back to homotopy groups. Homotopy groups. Um, okay. Here, one of the facts here is that so one of the facts here is that if X is a CW complex and Y2X is a covering space, is a covering space, then pi k of Y is isomorphic to pi k of X if k is bigger than equal to 2. Okay, and that is because that's why we had this, I told you, CW complex, because if X is nice enough, you have these map lifting property and homotopy lifting property. So if you work that out, then you see that the map p lower star is surjective as well as injective. Okay, that X is contractible.
Shamik,
Yeah,
there is a request to scroll the pages in a continuous fashion.
scroll the pages in a continuous fashion.
Manoj, maybe you can say exactly what you want.
Yeah, I don't know how to do that.
I mean, right now, the
Okay,
moment one page is done, it just goes off this page. I think that's what.
yeah, but I don't know how to do that.
Yeah, Manoj?
Maybe I'll learn it for the next.
Okay, thanks.
I mean, yeah. Anyway, let's stick to this. I mean, if you have if you want me to go back somewhere, I can do that. But yeah. Okay, let me just continue, and I'll just stop for a for little bit of time at the end. Anyway, I will share these notes on the ICTS website. So if you if you are missing anything, I think you will get the notes very soon on the website. Is that okay?
Yes, yes, thank you. That's enough.
Okay. So another property, um, yeah. Okay, another property which I want to state here is that you see, like there is a relative homology group. There is also a relative homotopy group, but it has slightly different properties. But but it can be defined in an analogous way, that using homotopy classes of maps. So basically what you do is, if you have a inclusion of spaces A inside X, um, you can define so then pi k of x comma a is this is defined to be like a homotopic classes of triples. Like you are you take the you take Sn will map to X. So this is a homotopy class of maps like this, of a map of triples. Sn maps to X, Um, so basically, if you take homotopy groups, it's like homotopy classes of maps of pairs if you consider the base point. Okay, so here you really have to use the triple, and then you take the upper hemisphere. Let me just write it as Sn plus for the upper hemisphere, and you take the base point. Okay, that should go to x a base point. Okay, and this is so oh, k and n are different. So I should say instead of pi k, this will be pi n of x comma a. All right. So it's a homotopy classes of maps between triples, and then you see that this pi 0, yeah, pi 0 is, I mean, that's really trivial. It's not, so it's a set pi 0, pi 1. These are sets of for pairs. So I should write it like this. So pi n of x comma a, this is just a set if n is less than equal to 1. This is a group if n is equal to 2, and this is abelian if n is bigger than equal to 3. That's the thing. Okay, so that's the way it looks like. And but you can easily deduce a long exact sequence. You can easily deduce a long exact sequence which looks like this: pi k of x to sorry, there will be pi k of a going to pi k of x, going to pi k of x comma a, and then goes to pi k minus 1 of a, and so on. Okay, and the maps are this pi k of a to pi k of x is induced by the inclusion. Pi k of x to pi k of x comma a is just a map which so it's a map which sends Sn to x. So you just squeeze the entire map into the bottom hemisphere and send the top hemisphere to the base point. That's the next map. And pi k of x comma a to pi k minus 1 of a is just a map which looks at the upper hemisphere, and the boundary maps to a. That's the other map. Okay, so I'll not say much about it. It's a bit it's like it's a tedious verification to verify that this is actually a long exact sequence. Okay, so that's another important fact. Although its importance comes later on when we talk about fibrations. All right. So the next thing is what are the computations you know? One thing is you know that pi k of Sn, it's easy to see that this is 0 if k is less than n. And that is because you could either use some differential topology or you could use simplicial approximation. So if you use simplicial approximation, you put a simplicial complex structure on Sk and Sn, and then every map after taking sufficiently many barycentric subdivisions give you a simplicial map. Um, so then so then you see that it has to miss some point, and if Sn minus point by stereographic projection is homeomorphic to Rn, which is a contractible space. So that's the thing. And then there is a theorem which of Hoff which says that pi n of Sn is isomorphic to Z, and the map here is F maps to the D of F. And this comes from the Hoff degree theorem, and a good way of proving that is using some differential topology. And actually, if you go greater than n, then this becomes very difficult to calculate. This is difficult to calculate. Not that nothing is known, but I will say very little is known. I mean, there are some systematic ways of doing it, but not much is known in this sense. Okay. So the next important thing is to define a weak equivalence. So a map f from x to y is a weak equivalence. Is called a weak equivalence. Equivalence. If it is an isomorphism on all homotopy groups, if it induces an isomorphism on all homotopy groups. Okay, and we write it like this. This notation we also use for weak equivalence, and it's a little bit of a confusion maybe if you are wondering that we use the notation for homotopy also, but we take that liberty here. Now we already defined CW complexes, right? So then there is this theorem of Whitehead's theorem, which says that a weak equivalence between CW complexes, equivalence between CW complexes is actually a homotopy equivalence. Complexes is a homotopy equivalence. So you see, homotopy equivalence has also this. You have the map the other way around, and you also have the fact that the compositions that there are these homotopies between the compositions to the identity. So it's a stronger condition than weak equivalence. It's easy to see that homotopy equivalence induces an isomorphism on homotopy groups, but the main thing is to go the other way around. So if you have a weak equivalence between CW complexes, isomorphism on homotopy groups, then we can construct the map going the other way around and all that, um, and show that there is a homotopy equivalence. Okay, so that's Whitehead's theorem. I don't have any time to prove, indicate how to prove such a thing. I'm just going to state the main features and go ahead. Uh, right, right. So the next thing I want to say is what are cofibrations? Okay, so a map f from A to X is a, is called a cofibration. It's called a cofibration if it has the homotopy extension property. Homotopy extension property. So uh, maybe you forgot this from the course in algebraic topology. It's a very useful property. It's used all the time. But let me just remind you. So what does this mean? This means that suppose I have a map from X to Z and a homotopy of the restriction from A to Z. So that means, let me just write it like this: X cross 0, and then I'm taking union over F with A cross 0, 1. Okay. So then uh, I can include this in X cross 0, 1. So the question is whether we can extend this to X cross 0, 1. That means I have a map from X to Z, and I have a homotopy of the restriction of the map to A. So the thing is whether I can extend the homotopy all over X. So that's the homotopy extension property. And if you can do it all the time, then that is called homotopy extension property. So if this dotted arrow exists for all the examples, then that's a homotopy extension property. Or equivalently, if it exists in the universal example, that means I should have a retract from x cross 0 1 back to this a cross 0 1 union f x cross 0. Okay, it's a cofibration if it has the homotopy extension property all the time. And the main example is if you put the main example here is example is if you put Sn inside Dn plus 1, okay, then you see that uh, my that place space, if I write Sn cross 0 1 union Dn plus 1 cross 0. So how will it look like? I will have the Sn cross 0 1 will look like a tube, and dn plus 1 means I should fill the interior. So let me use some other color like green, let's say, and that means I'm filling up the interior. And this inside dn plus 1 cross 0 1, this would look like again I have the filled tube. So the entire thing inside I should fill up with the green color. Okay. Okay. And so this should be a retract, and now you see that it's easy to make this a retract. You just pick a point and you project it. You pick a point on top, and you look at the straight line projection onto this thing. Okay. So from here, what you can do is that if you have a CW complex, if Y is a CW complex and X is a subcomplex of a CW complex of CW complex. If this happens, then then the inclusion is a cofibration. Inclusion X to Y is a cofibration. Okay. That you can check. It's just doing this Sn to Dn plus 1 example in a iterated manner. Um, okay, so that's a cofibration. And the next property is a fibration. Fibration. Okay. Fibration. So now a map P from Y to Z is called a fibration. Fibration. If if it has the homotopy lifting property, if there exists homotopy lifting in diagrams of this form. So if I take Sn, so I have Y to Z. Okay, this is my P, and then I have Sn inside Sn cross 0 1. So I have a map. I have a homotopy from Sn to Z, and then I'm restricting the map from Sn cross 0 to Z. So the condition is that that map lifts to Y. So this is my Sn cross 0 inside Sn cross 0 1, and I am putting the I have the condition that Sn cross Sn to Sn cross 0 1, this Sn lifts to Y, and then the homotopy lifting property will say that the entire homotopy must lift. Okay, so if this exists for all such diagrams, this map P from Y to Z is called a fibration. So this I should say this is a Sayre fibration. This is a I should really, if you are wondering about the correctness, this is a Serre fibration, and from here you can conclude that uh, I can replace. So if this condition is true for all SNs, I can replace all SNs by any CW complexes. So I can just take X and X cross 0, 1, where X is a CW complex. So just having the condition for Sn for all n is equivalent to having it for all CW complexes. Um, so there is another idea of fibration which is called a Hurewicz fibration, and there the condition is you should have this homotopy lifting for all spaces, and that's a different condition. Okay, and the main example here is that of a fiber bundle. The main example here is that of a fiber bundle. If you know that already, uh, it's still not easy to see this, but it's a proposition in the book, so it takes a little bit of work. Will be you will be able to deduce this, that if you have a fiber bundle over a space which is a CW complex, so the base of the fiber bundle is a CW complex, then then the fiber bundle is a Serre fibration. That's not hard to deduce, right? So that's an example. Okay, go to the next page. The importance of fibrations come from another thing, is that if I have a fibration, if y to z p is a fibration, then is fibration, and I assume that z is path connected. Okay, then this implies that all the fibers are homotopy equivalent. Are homotopy equivalent. It's just a trick with with the homotopy lifting property, which which was in the previous page. Yeah, it's just a trick with this property, homotopy lifting property with CW complexes. You just it's a trick. Will You will be able to show that all the fibers are homotopy equivalent. So you can put some f here. So if so I put start to be the base point, so I write this as f. Okay, but if I took any other point, I would get a something which is homotopy equivalent. So so we write a fibration usually like this. Uh, so the assumption is f is the inverse image of the base point. Okay, and then you can see that from the homotopy long exact sequence, one can show that the relative homotopy groups, this is actually isomorphic to pi k of z. This is another application of homotopy lifting property. You can show this. You can show this, and that gives me a long exact sequence. Long exact sequence pi k f to pi k y to pi k z, and then that goes to pi k minus 1 f. So fibrations give you long exact sequences on homotopy groups. That's another nice property of fibrations. Okay. Okay. Now let's go to the next point, um, which is the next point to remember is this. So now let's start with a map here. Okay. Yes. Okay. Let's look at this map, uh, and Many of you would be familiar with the mapping cylinder construction. Mapping cylinder MF. Okay, so what is that? That is, you take x cross 0, 1, uh, and you take disjoint union with y, and you identify x comma y 1 with f of x. Okay, so the property is that this mapping cylinder of f, actually I have this map to y, which takes x comma t to f of x. Okay, and this map is a fibration and a homotopy equivalence. Homotopy equivalence. Okay, in fact y is a deformation retract. The inclusion of y as is a deformation retract. So this is x comma t goes to f of x. I should also said where y goes. Y will just go to y. Okay, so this is a fibration plus homotopy equivalence, and I can write input x. I have a map from x to mf which sends x to x comma 0. Okay, so that's the top. So if you look at the mapping cylinder, it looks like this, right? So y is in the bottom. This is x cross 0, 1. So I have put x on the top. Okay, so that's the map. So this map, x goes to mf, and then that goes to y. So this map here, this actually is a cofibration, and this map here is a fibration plus homotopy equivalence plus weak equivalence. Okay, so that's one way of breaking up this map. So you can break this map into a cofibration followed by fibration weak equivalence. Okay. So the next point is, if I look at fibration from the point of view of fibration, I have this map x to y f, and now I can form E of f to be the set of all x comma gamma. Uh, so x is an element of x, and gamma is a map from 0, 1 to y. So you can give it the compact open topology such that gamma of 0, so that's where the path starts, that should be equal to f of x. Okay, now I have a map from E of f to y, which takes x comma gamma to the value at the other endpoint, gamma of 1. This is a fibration. It can be proved that this is a fibration. And the other one is, I have a map from x to E of f, which takes x and sends it to x comma f, sorry, yeah, x comma constant path at f of x. Okay, so it turns out that this one is a cofibration plus it's a weak equivalence. Okay, so you see now this is another way of factoring this map, x inside E of f to y. This is my map f, and this one is cofibration weak equivalence, and this one is fibration. Okay, so the first map here is cofibration weak equivalence, and the second one is fibration. Okay, so it's a very useful fact that you can do this. All right, so that's one of the nice properties here. So you have this, you have a you have something called a cofibration, you have a fibration, and given any map between two spaces, you can either factor it through a as a cofibration followed by fibration weak equivalence. That's using the mapping cylinder, and the other one is using this E of F construction. You can factor it as cofibration weak equivalence and then a fibration. Right. Let's now go to the next point. Uh, the next point is the theorem. This is called, this is CW approximation. Okay, so this says that for every space X, there exists CW complex Y plus map Y to X, which is a weak equivalence, which is a weak equivalence. Okay, so for every space X, there exists a CW complex Y plus uh, map, which is from Y to X, which is a weak equivalence. So the proof is, I mean, it's a it's a simple thing that you have to just attach cells one by one so that you get the right homotopy groups. And again, I'll not go into the proof, but there is an important consequence here. So consequence of this CW approximation, and plus also of course Whitehead's theorem earlier, which says that every uh, um, it says that every uh, weak equivalence between CW complexes is actually a homotopy equivalence. So what is the consequence of this? So remember, I started this lecture saying that I wanted to study topological spaces up to homotopy equivalence. So if I want to take look at top up to weak equivalence, this is uh, equivalent to this category, equivalent to the category um, H, where objects of H are CW complexes and morphisms of H are homotopy classes of maps. Homotopy classes of maps. Okay, why? Because every topological space is weakly equivalent to a CW complex, and a weak equivalence between CW complexes is a homotopy equivalence. So if you invert the weak equivalences between CW complexes, you only get the homotopy classes of maps. I mean, the after that, applying that in equivalence, you see that a map will be equivalent to anything which is homotopic to it. That's all you get. Okay, so I have still a little time, and I actually had a lot of other things to say, but let's see. So there is one thing which I want to say here before I stop. So this was one point. Another point is about this uh, like what is computationally useful here. So if you want to compute anything, like you want to compute, let's say, homology or cohomology, there is a certain thing called a cofiber sequence, which is very useful. Uh, so let me just describe this. So this is also called Barratt Puppe sequence. So suppose you have a map from x to y. So then you can take the you can attach y to the cone of x along the map f, and that is called the mapping cone of f. So this is nothing but y union cone of x along the map f. So x is in the bottom of the cone. Okay. Now if you do the same construction on this map y union cone of f, so then you will get uh, you would end up attaching a cone to y, and what you will get is the suspension of x. Okay, because the y is coned off, so that means what you get is the suspension. And then if you do the same thing to this map cone of f to suspension of x, what you would get is the suspension of y, and that's how it goes on. Okay, so the next one is the suspension of cone of f, and you realize that if you apply the functor homotopy classes of maps to w star, this kind of thing on this sequence gives gives you something like this, gives you homotopy class of maps from x to w, then y to w star, then cone f to w star, and so on. Similar construction, right? So this if I so so whenever you have base classes, they are always pointed sets. So there is a null map, and if you take this composite here, this composite is just null. Okay. Additionally, you have this property that if you have element here which goes to the null thing, then there exists some thing over here which goes and hits that element. Why is that? Because if it so that means what does it mean that this y goes to null? That means I have a map from y to w which is null homotopic when I restrict to x. So that means it factors to the mapping cone. Okay. So now you see that this is almost like a long exact sequence. If all these homotopy classes of maps were abelian groups, then this would be an honest long exact sequence. Okay. So that's the thing, but they may not be abelian groups. They are just sets with a point. So it's not exactly a long exact sequence. You can call this a long exact sequence of pointed sets. Okay, and yeah, well, the comment I made is that if you look at this sequence and you apply cohomology, then that gives you a long exact sequence. Okay, and another analogously for fibrations, you have this fiber sequences. Uh, Yeah, I will just say this and stop. Fiber sequences, it's entirely analogous. You can start from x, y, f, and then you do the E of f construction. And remember, E of f is homotopic to x, and then you take the fiber. So this is this f. This is called the homotopy fiber. So what is that? This is the fiber of E of f to y. Okay, the E of f construction I just did before. Now it turns out if I apply the same construction to the next map, then what I get is the loop space, base loop space of y. And the next one gives you the base loop space of x, and so on. And again, here, if I apply this functor, this gives a long exact sequence of pointed sets. Of pointed sets. Okay. So, these two sequences are very useful computationally, but I don't have time to really say much more about that. So I think I will stop there. And sorry for. I wanted to stop 10 minutes earlier, but anyway, I still went a little over time. Okay, so let me stop there.
Thanks, Shamik. Uh, if there are any very quick questions, we can ask now. Otherwise, we'll wait for the discussion at the end of the next talk. So if you have any quick questions, please raise your hand.
The comment about applying cohomology to the cofiber sequence is that it gives you a long exact sequence. So you have, so it's just basically the long exact sequence of, I mean, X, so it will be cohomology of Y. So cohomology of Y to cohomology of X, and the next one will be the cohomology of X comma Y, which is the, sorry, Y comma X, which is the cohomology of the mapping cone, reduced cohomology of the mapping cone. You realize that here. Yeah, I don't want to write here because I think I will send the slides to ICTS. But you see, cohomology of Y comma X is nothing but the reduced cohomology of the mapping cone.
Shubhajit has a question in the chat.
Yeah, it the yeah, it is there in Hatcher's book, chapter 4.